I'm super excited to be here and very excited to talk to you about this lovely talk and about resilience, which I know Amy already previewed a little bit earlier today. So systems resilience depends on the ability to respond and adapt to changing conditions. And this adaptation really depends on the ability to learn about the reality in and around the system, especially as it evolves. In software, this is non-trivial because our software systems are complex, they're sociotechnical, they're difficult to reason about. We really don't have software that can adapt and evolve on its own. Humans are the mechanism for adaptation in our complex software systems. It's really only humans that can reason about the system and then change it. SREs in particular serve as a really critical mechanism to learn about the system and then inform that adaptation. This means it's important for us to really understand systems reality and then also complete a feedback loop that drives change. And to inform this endeavor, the question we're going to explore together today, I'm really excited to, is how can SREs align their mental models of the system with reality to sustain resilience? Part one, we're going to cover adaptation in complex systems, my favorite topic, to set the stage for part two, the necessity of simulating scenarios like conducting chaos experiments to expose a very messy reality of our systems. Part three, we'll discover how decision trees can help us visualize our mental models and refine them and system design over time. Let's dive in. Starting with adaptation in complex systems. Complex systems involve a lot of variables, so they can present a large variety of possible states. And this means prediction is just impossible. With so many possible future states in the system, there's really never just one path that will lead to a particular outcome. Even trickier, and you probably experienced this yourselves if you've tried out a manual sequence of steps and then what happened, the outcome's totally different. Performing the same sequence of actions in a system may result in a different sort of outcome. So I like to think of it as getting from point A to point B in a complex system as less as the crow flies and a lot more as like the cat zoomies around. So if we can't predict, that means we can't use determinism to stop bad things from happening. It means we have to adapt instead. Because the reality is failure is inevitable. It's a natural part of complex systems as they operate. It's really a feature. I know we think of it as a bug, but it really is more of a feature of complex systems. That's why we need the capacity to adapt to failure. And really what we see across all these sort of complex systems domains is that successful complex systems are adaptive. They change and evolve over time and space, especially in response to evolving conditions and changes in their external environment. Key concept to remember is adaptive capacity, which again, Amy talked about a little bit earlier. So adaptive capacity reflects how ready or poised a system is to change how it works. Its behaviors, models, plans, processes, practices, to change all of those things so it can continue to operate in a changing world featuring surprises and other vagaries. Resilience reflects this need for sustained adaptation, that we must prepare for failures and opportunities alike to thrive. More formally, resilience is defined as the ability to prepare and plan for, absorb, recover from, and more successfully adapt to adverse conditions and events. Okay, how do we think about the need to sustain resilience? What do we need to do it? There are 5 common features that define resilience, which we can frame as a resilience potion for fun. So the first ingredient is defining the system's critical functionality. This is the system's raison d'etre. I don't know French, but if you're French, I'm so sorry for the pronunciation. But what we care about is how the system performs its core operations while under stress from deleterious or nefarious events. This is represented by milk in the resilience potion. I don't recommend spilling it everywhere if you actually try making this at home, but it is a very splashy, pun intended, picture. Right, the second ingredient is defining the system's boundaries of safe operation. So these are the thresholds beyond which the system is really no longer resilient to adverse conditions. A system can absorb changes in conditions only up until a certain point and then stay within its current, healthy state of operation. This is represented by dried hibiscus in the potion. The third ingredient is observing the system's interactions across space-time. So because complex systems involve a lot of different components interacting with each other in all sorts of ways, the resilience can only be understood through system dynamics across space and time. Different behaviors can unfold across time and across the topology of the system. This is represented by cacao beans in the potion. It's a fun fact, you have to ferment them. The fourth ingredient is fostering feedback loops and a learning culture. That includes a blameless culture. Resilience really depends on the ability to remember failure and learn from it. Feedback loops, which if you don't know, outputs from the system are used as inputs in future operations. Those are essential for systems resilience. And this is represented by chili peppers in the potion. Then the final ingredient is flexibility and willingness to change. This is that adaptive capacity we talked about earlier, which is just so amazing. So we need to sustain this flexibility over time too. We have to keep the system flexible enough in response to all of the sorts of changes and operating conditions we experience every day. This ingredient is represented by very squishy marshmallows in our potion. If you can piece it together, this is like a very redolent, tasty, spicy hot chocolate when you do everything. It's great for after incidents. It really soothes the soul. How does this look in our computer systems? Like, what is adaptation even in our computer systems? In a kind of strict tactical sense, adaptation in computer systems is the ability to respond to unexpected input, uncovered design flaws, unexpected failures of components, unexpected shifts in flows and volumes. But this neglects the human element. In a wider sense, when we think about it, we have sociotechnical systems with humans executing their processes and machines doing the same. Humans and machines are constantly influencing each other. Humans iterate on new and updated programs for the machines based on feedback received for the machines, or from other humans, when they're asking for the system to function in a different fashion. When machine processes fail in ways that are noticeable, humans jump in. Again, to a large extent, the humans in the system are the mechanism for adaptation, just like genetic mutation in biology. The key point is software has very limited ability to adapt on its own. Humans are the primary adaptive capability. Without humans, including SREs, the system will fail over time. Take an example from InfoSec. I think most of you, raise your hand if you're familiar with the Log4Shell attack. Okay, yeah, I figured probably a lot of you were involved in remediating this. So when that attack unfolded, right, it was an emergency, all hands on deck kind of situation in many organizations. But I certainly think that the real world harm was pretty low, or at least relatively low, compared to what it probably could have been. And you, if you were involved in the recovery efforts, that means you were the mechanism for adaptation to this unwelcome surprise. Amy talked about those unknown unknowns. That's exactly what this was. You helped adapt. So how we learn influences how we adapt to stressors and surprises and adverse conditions in general, and our learning is based on our assumptions about the system and the reality around the system. The software we design, build, and operate reflects our mental models. So what are mental models? They are our cognitive representations of external reality. It means in our heads, like this little guy's adorable little head, we hold a smaller scale model of how we think a system works. Of course, these representations are going to be incomplete and inconsistent because we are human. We're fallible. We have finite compute power in our heads. Mental models are also dynamic. They change as the situation changes, which makes them dependent on context. They're not static entities. Understanding our system's context is really no small feat. It's especially difficult to understand systems that are the result of years of iteration, like this fractalizing dragon spiral dragon curve here, rather than a single upfront of design. When it's this nice little right angle up at the top left, great, we can definitely model it. But by the end, it's a catastrophe. This is why surprises feel especially fraught in our messy, complex software systems. So I love this quote by evolutionary biologist Lynn Margulis, who described the element of surprise as the revelation that a given phenomenon in our environment was, until this moment, misinterpreted. In essence, you can think of a surprise as an open challenge to our mental models. And this means, as Dr. David Woods very pithily puts it, we must prepare to be surprised. Ultimately, you can't fully know what hazards lurk or what resilience properties emerge except by observing how your system behaves once it's running. You can think of resilience as a verb, which means it can only be revealed in the event log of reality. We can observe how our systems really respond to adverse conditions through resilience stress testing with chaos experiments. Okay, how many people in here have heard of chaos experiments? Okay, great, good, glad there's a good basis. So our goal is really to uncover baffling interactions, as they're called, in our systems by revealing how the way the world actually exists compared to how we think it exists, or how we would like it to exist. We can do so through chaos experiments, which is basically just resilience stress testing for software systems. If you don't know about other domains, a lot of them, pretty much all of them, call it resilience stress testing. If I had a time machine, I would go back and change it, but chaos is also cool, so we're going to stick with that. So if we can continually reconcile our mental models with reality, then we can continually improve system design and ensure our architecture can meet our reliability and security needs on an ongoing basis. I think a considerable portion of our incidents are actually a result of our mental models of the system not reflecting reality. And a lot of incidents are much more troublesome to debug and to resolve as a result of our incomplete mental models. But experiments generate evidence of how much our mental models deviate from reality. How difficult was it for us to gracefully recover from failure? Again, when I say us, it is both the machines and the humans in the system. Experiments will reveal both the socio and the technical impacts. You can induce adverse conditions and adverse scenarios via chaos experiments to learn about the behavior of the system under stress more quickly. If we serve as the mechanism for adaptation in our, again, very messy, complex software systems, we need to continuously learn about our system's context, right? This experimental capability really supports this continuous learning. So arguably, conducting experiments is really the only way we can realistically keep up with our rapidly evolving environments. Importantly, chaos experimentation appreciates the inherent interactivity in the system across space and time. We conduct system-level adverse scenarios rather than evaluate parts of the system in isolation. This, again, very messy reality of complex systems, there's just not enough time or energy available for us to individually mentally model or experiment on every single component to identify weaknesses. I think that many weaknesses only emerge really once the system is assembled and has activity in it, once it's in effect this kind of living, breathing thing. By the way, this doesn't mean we have to experiment in production. We actually don't recommend that. If you're starting out, start in staging, it's totally fine. But wherever you do experiment, it does need to feel lifelike. But what this means is that we can fix things in production by learning about adverse conditions via experiments. Again, this is very explicitly not about breaking things in production. It never has been, by the way. The point is to make things better. Unlike traditional testing, including things like fault injection, which I'm a fan of, by the way, but with chaos experimentation, we're far more curious about assessing the nature of the system and its interconnections. We're far more curious about how the system behaves in adverse conditions than we are about how it responds to, say, a specific type of disruption. Actually, this brings us to a natural question. I'm sure you all maybe have already thought of this and typing up in Slack, but I get this a lot. How are chaos experiments different than any other kind of test? This is a leave behind. You don't have to read it now. This is very much so you can look at it later, sound super smart in your meetings or cocktail parties, if those are still a thing. Well, let's focus on the chaos experiments column. So chaos experiments support resilience. They are sociotechnical. They include humans as part of the system. They are systems focused. They're capable of being run in production. They're random or pseudo-random. They reflect adverse scenarios. They're also about observing and learning from failure and about n-order effects. To make this a little more concrete, let's explore how an experiment looks in practice using the example of a manufacturing company, not the type of company you typically associate with this, highfalutin, newfangled stuff. All right, consider a manufacturing company that maintains a physical parts database for its manufacturing sites on both the East Coast and West Coasts of the United States. The parts management system runs on the East Coast, making it the primary site. I'm from the East Coast, so I had to, sorry, West Coast people. And it broadcasts data about the parts to each site via database replication. Most of you may know this, but for those at a different place in their software journey, data replication is often used for things like disaster recovery. But a core property of replication that organizations often want to preserve is the ability to operate the system with data that is stale, but not too stale. So if replication is 10 seconds behind, maybe that's acceptable for your needs if it's unlikely that the state will have changed too substantially in those 10 seconds. Naturally, the manufacturing company wants to understand how their systems behave when replication is severed or when it gets too far behind. Their mental model is that each site can function independently, but how loosely coupled are they in practice? Does the system notice that the data is operating on is stale, or Is someone alerted? And if they're alerted, do they actually respond to the alert? Are they able to recover from it? Can operators somehow use inventory that doesn't exist? And if so, what ill effects does that cause? Like, does it stop the production line or cause something else? These are all very worthy questions that inspire an experiment to answer them. So a potential experiment our manufacturing company could conduct involves the adverse condition of severing the database replication between the two sites, just like this beautiful volcano. So when the connection is restored, they want to verify that the secondary site correctly incorporated the changes that were made at the primary site during the outage. Let's say their hypothesis was proven incorrect. Replication didn't work, requests continued to be served from the West Coast. Not very stonkly. It means there was tighter coupling than they believed, and the secondary site on the West Coast could end up serving a big pile of nothing, basically. That could inform a design change, like halting the West Coast data center if it's not cut up to the primary, again, the East Coast. And that's rather than letting the West Coast data center just proceed and fail while draining money. Nobody likes draining money. Now, let's assume they rerun the experiment after this design change. This time, let's say they learned a few surprising lessons. So the good news is that when they reconnected the sites, the replication caught up quite quickly, maybe faster than they expected, which suggests that they gained both looser coupling and greater efficiency from that design change. The bad news is they weren't alerted about the replication lag, the fact that the data wasn't up to date, even though they thought they had alerting for that scenario. Their mental model was, in essence, violated, but that presents another opportunity to redesign and refine, and then, of course, run the experiment again. This kind of disruption, by the way, can totally include security issues, which we'll turn to shortly as an example, since they can become reliability problems. With chaos experimentation, we really just want to understand how systems recover and adapt under adverse conditions, again, like degraded or disrupted functionality. But these adverse conditions can take many guises. I like to think of it as, piecing together a mosaic to understand the behavior of the system. And each sort of scenario you conduct or experiment you conduct helps fill in that mosaic. Exposing those baffling interactions we talked about, that complexity that can lead to the most pernicious failures, it's also important from a security perspective. So it's important from a security perspective because attackers love to take advantage of interactions and interconnections and components to compromise a system. So think about SolarWinds and CodeCov. I'm guessing most of you have heard of those. Attackers love both of those because of the connections each product had into their customer's infrastructure. Even something like social engineering you can think about as exploiting the interaction between the human and the machine. So attackers really aim to understand information flows, layers of the system's fractal, that dragon curve we showed earlier. And in general, they think about boundaries and interconnections so they can figure out how to leverage them for, their nefarious schemes. This leads us to exploring some examples of how chaos engineering applies to security, because it's absolutely something that can fall under y'all's purview too. Amy talked about this. Resilience is really your mandate, right? If you care about reliability. And the thing is, if we want to sustain resilience, we also have to sustain resilience to attacks. In a rather obvious naming scheme, this is known as security chaos engineering. What is it? So security chaos engineering, aka SCE, is a sociotechnical transformation that enables the organizational ability to gracefully respond to failure and then adapt to evolving conditions. SCE uses the practice of continual experimentation to verify that our systems operate the way we believe and then improve our system's resilience to attack. More simply put, you can think of SCE as helping align our mental models of the system with reality. How do we create a security chaos experiment in practice? Like any scientific experiment, which are always fun to do, we start with a hypothesis. Our mental models are actually the basis of our hypotheses. We generate hypotheses by making assumptions about reality to inform our experiments. In particular, we can target our "this will always be true" assumptions. I created, much like Gartner, the terrible acronym of TWAPT assumptions, which is just horrible to say, but it's kind of fun too. So we can think about our TWAPT assumptions. These are the things we think of as our invariants in the system. These sort of assumptions can manifest in every part of your stack at basically every level. Like, parsing this string will always be fast, or messages that show up on this port will always be post-authentication. An alert will always fire if a malicious executable appears. and so on. I'm sure you all are now having flashbacks to things that you're now thinking about, things that you thought were invariants and weren't. So from these assumptions, we craft a hypothesis. An example experimental hypothesis that overlaps reliability and security is, if a user accidentally or maliciously introduced a misconfigured port, we would immediately detect, block, and alert on the event. As you can see in this example, which is from Aaron Reinhardt, he actually conducted this in reality, so this is the true results. This hypothesis might be disproved after the experiment. The firewall didn't detect or block the port change. In fact, fun fact, you know that line, 60% of the time it works every time? The firewall only worked 60% of the time in doing this, so firewall is a great example of this. The port change didn't trigger an alert, but we did learn that our commodity configuration management tool caught the change and alerted responders. This is kind of a baffling interaction that actually surprised us in a good way. Our existing mental model was disproved, and once again, humans really served as the mechanism for adaptation to figure out how to recover from this. So what other kinds of experiments are relevant to SREs? Again, there's really, I cannot overstate the overlap of SRE and security that no one talks about. By the way, security doesn't realize this. I am trying to teach them, but you all get to hear it first, so be excited. So what kind of experiments can we conduct? Like disabling non-critical roles and functions in APIs, disabling resource limits, generating large loads on specific availability zones or data centers, turning off API authorization. Or we could inject canary credentials or keys into code scripts or logs. We can inject expired OAuth tokens into builds. There's also overriding build logs, deleting log files. That's foreshadowing, by the way. Disabling access to DNS, exfiltrating large volumes of data, like data egress. Or creating and scheduling new jobs via the automation server script console, and my absolute favorite, time traveling on a host. That is changing the host time forwards or backwards. Cool stuff, right? So all of these experiments will expose how our socio-technical system behaves in these scenarios end to end. Not just whether a particular component, detected, logged, alerted, forwarded in the security lingo, but also how the humans interacting with the system behaved. When we reveal the resilience properties of our complex software systems, how do we capture this knowledge? That's really important. We can capture our experimental knowledge with decision trees and use them to refine our mental models. So reasoning about the potential range of behaviors of systems under stress, whether expected or unexpected, is really difficult. But since resilience is a verb, the question is not, is the system resilient, but instead the resilience of what to what. We can use decision trees to describe and explore the resilience properties of the system in the context of specific events, stressors, or surprises. I'm gonna guess not everyone here is a huge game theory nerd like I am, so what are decision trees? Decision trees are a visual representation of different actions or events different entities can take in a scenario, like attackers versus defenders in the security context, but it can even be like machines and machines in the reliability context. You can use decision trees to navigate potential failures, the limits of your understanding, which is the limits of your mental models, and where to apply design or process changes to nourish resilience and reliability. Let's walk through an example tree and then see some real-world ones to ensure our understanding takes root. Promise that's the only tree pun, but it is a very good one, I think. All right, to show you how we look before we dive into an example today, this is the OG security tree I created involving a scenario of sensitive video recordings in an S3 bucket. So all the trees we'll look at today are generated by Deciduous, which is an open source decision tree generator, which uses YAML for your convenience, as well as being able to import some GitHub GIS. And that started out with security decision trees as the primary use case, but it works really for any problem domain like SRE stuff, or my favorite case that totally didn't happen, where to store your YubiKey so your cat doesn't either try to eat it or like otherwise yeet it off your desk, right? That's a very real failure scenario. So in general, decision trees map adverse events and potential mitigations and visualize how they unfold across space and time. Events usually unfurl in some sort of sequence and in different sequences depending on the contributing factors, things like mitigations even. We can capture all of these diverging paths in our decision trees. In the context of security, when attackers want to compromise a specific asset, attackers have multiple paths and avenues at their disposal. Creating a decision tree helps you map out these attacker choices and visualize what paths they're likely to take and what kind of methods they're likely to employ to get to their goal. Disclaimer time. Keep in mind here that our goal is to document our mental models of the system, and specifically system dynamics in a specific scenario for the purposes of proactive experimentation, to start filling in that mosaic that we talked about. There are almost assuredly going to be gaps in our decision tree and our mental models and reality, right? The point isn't perfection, though. The point is iteration that keeps us honest about our mental models as they, the system, and the system's context swirling around it, as all of those things evolve. The reason why we perform chaos experiments is to refine our mental models. It's to understand system dynamics and interactions better. So in this adverse scenario we're going to cover in depth today, the outcome is missing logs, because that just sucks, right? I chose to create this one because if you are responding to an incident and logs are missing, that's just a really bad time. So the first branch of the decision tree, when you create it, should reflect the most obvious and expected events. We can call this the YOLO branch, since it usually involves an adverse event that's kind of like an obviously bad thing to do, or something like inaction. So in this case, there are actually a few YOLO actions and YOLO branches, which is like giving all your hosts the same host name, misconfiguring the log daemon, blocking network egress, and forgetting to install the log daemon. So for any of these, not mitigating them results in the adverse condition of missing logs. That's why they all go to that bad outcome. Now let's zoom in on the YOLO branch of the misconfigured log daemon. There are actually two adverse events that are possible here. Probably more you can tell me about after, like chat about it in Slack if you aren't already. So the two adverse events are expired TLS certificates, everyone's worst nightmare, and configuring the wrong path to gather logs. Either one is going to result in missing logs, but it reflects our first fork in the tree, since addressing each might require different mitigations. The obvious mitigation for expired TLS certificates is to monitor the root certificate store. For configuring the wrong path, we have two potential mitigations. So one, we can standardize log paths so all production services write to the same path. Second, we can write smoke tests to verify that logs are working as intended. After every mitigation you assume are put in place, like these, you should always ask how the system might respond to it. Like, could there be other adverse events that kind of unfurl after it? This is especially important when creating security decision trees where attackers are performing the actions. So let's look at another branch to see what we mean here. So the obvious mitigation for forgetting to install the log daemon is adding the daemon in the base image. Pretty straightforward. So we did it. But wait, it's still possible for us to forget to start the log daemon, which is a very big oof. There are a few mitigations for this one. So we can obviously just start the log daemon. We can monitor the log daemon, or yet again, we can write smoke tests to verify that logs are working as intended. Okay, we started the daemon, but what else could go wrong that might still result in these missing logs scenario? There might be so many logs that it fills the disk, so logs are no longer produced. There might be so many logs that are being produced that we can't actually ship them, like they're being produced faster than we can ship them. Log timestamps might also be wrong, whether due to an incorrect host clock or incorrect parsing of log timestamps. That's like a lot that can go wrong, so what do? Well, we start brainstorming together. So for filling the disk, we can monitor and alert on disk usage. And if we're producing logs faster than we can ship them, we can maybe reconfigure the app workload to log fewer events. If you're brainstorming this with colleagues on other teams, which I highly recommend, it's a great way to kind of like bond, maybe they chime in that we could create an integration test that checks that our log levels are as we intend. Someone else chimes in like, hey, we can actually run an NTP daemon for the incorrect host clock. Then for incorrect parsing of the log timestamps, maybe we want a standardized logging library, which we maybe want for a bunch of other reliability reasons anyway. Now we can zoom out, see all these amazing flows in action to see how we capture a mental model in the decision tree. What I love about creating decision trees with teams and organizations is that you usually get a very visual sense of what mitigations might help. So like here, smoke tests to verify working logs. It's connected to quite a few things. It helps mitigate quite a few things, so we probably should invest in them. If you're having a really difficult time getting buy-in for stuff like that, and I will say a lot of times on these decision trees, it's mitigation like smoke tests that are often left as like, yeah, okay, we'll get around to it, or it's not the most important thing. This kind of visual can really help you get buy-in because it makes it really salient, like how much it's addressing. Then also each iteration or interaction that you see here can be assessed by conducting a chaos experiment, which we'll come back to in a minute. As another reliability-related example, here's a very simple decision tree for the adverse condition or adverse scenario of unrealistic distributed traces, that traces don't reflect reality. The yellow branch from which all the others flow is not having any trace IDs. The obvious mitigation is adding trace IDs, but there are other events that flow from there too. And for fun, there is no way you're going to be able to read this on the slide, but I will explain what it is. So this is a Rick and Morty episode called The Thingsploitation Spectacular, if you don't know it. Basically, the main character, Rick Sanchez, is trying to receive a federal pardon, and the US president is the defender that's implementing mitigation. It involves like them turning into turkeys and all sorts of stuff. It's like surprisingly elaborate. I actually have a blog post on this that's in the Deciduous repo on GitHub, so if you want to scroll through, you can. But it's really just to show decision trees are really flexible. You can model all sorts of scenarios. And crucially, it prompts you to think about how events unfold in adverse scenarios so you can prepare for them. How do we apply these decision trees in practice in our SRE work? A decision tree should cover all issues or close to all issues relevant in your system, including ones that already have mitigations, because contexts change over time. Probably many of you have had the horror story of when a mitigation has decayed. You haven't realized it, kind of like the fire extinguisher that has long expired. Think about our log example, like maybe an operator stopped the log daemon while doing maintenance, or maybe too much might be logged as changes accumulate over time, which means logs creep ever upward until it starts filling the disk. So decision trees can visualize these assumptions that we take for granted to inform experimental hypotheses that allow us to verify that our mitigations are working. That means that our mitigations aren't going to decay. In general, a decision tree can capture your system architecture and the flows within the system. This is also in addition to any gaps that exist where the system is maybe unprepared for a particular kind of stressor or surprise. Again, we want to thoroughly capture our mental models and evolve them over time. Chaos experiments form a just beautiful feedback loop with decision trees, with the decision tree indicating potential experiments, and then experiments leading to updates to the tree. It's just like a beautiful, beautiful situation. So for example, we could inject more logging statements as an experiment to see how our system behaves end to end. So remember, socio and technical parts of the system, both how the humans and the machines respond to this deluge of logs. Maybe there are mitigations also that help us that we didn't realize were there, like that configuration management tool that blocks a change. Maybe there's an n-order effect we didn't anticipate, like the log example, like maybe there's an outage in another service because of the log deluge. All of this is really to bring you, the socio part of the system, towards a more accurate mental model of it. That way you can proactively anticipate and mitigate stressors and surprises. So it's pretty clear that decision trees are essential for informing improvements during the initial design phase of a feature or system when it's first conceived, but they also shine as a tool for continuously refining system design and architecture to optimally sustain resilience. When thinking through changes to a system or feature, you can consult your decision tree to see how the proposed changes would maybe alter the relevant interactions in the tree. From there, you can understand how the system's resilience to a stressor surprise might change, whether that's like to an attack or resource saturation or whatever else reality has in store, because we all know like we're continually surprised by reality. Decision trees are also invaluable during incident reviews and retrospectives or postmortems, if you still call them that. So you can pull up your relevant decision tree and see where your assumptions held true or false. Also great for a blameless culture because you can point to the tree and it was the tree that was incorrect, not anyone in the room. You have this kind of like inanimate object that you can kind of deflect some of your attention on. So what are some of the questions you should ask as you do these kind of incident reviews? There are quite a few. So did events unfold in the flow modeled in the tree? Perhaps one part of the system failed over to another sooner than expected. In a security example, this might be phrased as, did the attackers take any of the branches modeled in the tree? Did your mechanisms alter the flow or sequence of events as anticipated? Maybe monitoring disk usage didn't mitigate filling the disk because there were just too many alerts for humans to respond quickly. Again, with like things like production pressures, I've heard of some teams where they're getting just way too many alerts for a human mind to comprehend. maybe monitoring just doesn't help. In a security context, the question is, did the mitigations alter the attacker's path as anticipated? So what actions or events were just straight up missing from your decision tree and from your assumptions? Were there any second or n order effects that you missed in your mental model? Were there also any intermediate events or things like attacker actions that you didn't capture? Were there any mechanisms or mitigations that surprised you and you didn't expect to help, but maybe did? In our example, maybe billing alerts was actually the thing that got you to recover the system and alerted you about the log deluge faster than your actual monitoring for it. In a security context, this is kind of like, did the attacker encounter any stumbling blocks that you didn't realize served as mitigations? Like maybe your use of immutable workloads for reliability purposes made it difficult for attackers to run their payloads because they expected to be able to write to disk. You can also document decision trees before you ever conduct chaos experiments, because they can serve as hypotheses for the chaos experiment. So in our example, you could craft a hypothesis like, in the event of an expired TLS certificate, we'll be notified by our root certificate store ahead of the expiration so we can update it. Famous last words, right? But you can experiment this. You can inject an expired cert or soon to expire cert to verify the hypothesis. If the hypothesis is disproven, you now have extremely actionable evidence to either refine design or practices. It's really great. You can also conduct an experiment to assess the efficacy of a potential architectural change by conducting it in a staging environment. So in our example, remember we proposed, like, maybe we standardize the log library. Well, run a version with that change in staging, conduct an experiment, and verify that it actually mitigates that adverse condition. Again, even if it's not a perfect test, it's still way better than the like back of the napkin sort of, or back of the envelope sort of estimate that we mostly conduct today. You can also do the same to see if someone's draft PR matches requirements and meets their expectations. And all these iterations in turn can really refine the decision tree, and it enumerates potential mitigations and what their efficacy is likely to be. It also means you can keep your mental models fresh with experimental evidence. One thing I definitely see in security land, and I know sometimes happens also on the SRE side, is that sometimes organizations get maybe a little complacent. They're like, well, we haven't had an incident in a long time. Do we really need to invest in this? Experimentation is kind of like injecting that in a healthy way on an ongoing basis, so you're more incentivized to start fixing things in production. So when you start your experimentation at each kind of functionality point in the decision tree, starting with the easiest branches lets you continuously verify that all the kind of obvious and expected failures or hazards are sufficiently eliminated. Think about some of our examples earlier, like not starting the log daemon or just not having trace IDs. On the security side of things, this is often called like the low-hanging fruit for attackers. So once you feel confident in your system's resilience to the more obvious failures, you can move to the branches that involve like more of the unexpected changes, like those that require a confluence of failures, multiple things going wrong at the same time in your systems, or things like higher attacker effort. Really, only after a very extensive period of chaos experimentation with design and strategy refinement based on the resulting feedback loop, do you even move on to trying to tackle the like super weird esoteric failures branch. It's also possible your organization never really gets there because for most organizations, there are tons of changes all the time. You have stuff to continually experiment against. Honestly, few organizations ever will get to like, in security world, that's like the 0-day path. Like where just an attacker's using like a chain of 9 0 days, like it's very unlikely. Focus on the easiest branches, the more expected failures. Right, we've had our roots watered with the ways of resilience, so let's summarize so we can go from here. Our software systems are inherently sociotechnical. SREs are the socio part, and they're critical for the system's adaptive capacity, and ultimately, its resilience. To adapt successfully in a complex system that is always evolving, we must continuously refine our mental models of the system. We have to continuously refine our understanding of the system's reality. We can expose gaps in our understanding where there are baffling interactions or accidental complexity and other surprising properties through chaos experiments. And they're the simulation of adverse scenarios to observe how the system behaves over time and across the topology of our system. Then with this evidence in hand, very exciting, we can capture and visually represent our evolving knowledge in decision trees. By documenting our assumptions and our evidence, we can inform iterative design improvements and complete the feedback loop on which resilience and reliability depends. If you enjoyed this, you're going to love my upcoming O'Reilly book, Security Chaos Engineering, Sustaining Resilience in Software and Systems. It's going to be out next month. Dying for y'all to read it. Please nerd out with me. I need more nerding out in my life. With that, thank you so much for your time and attention.